Alright, hey everyone, this is going to be a walkthrough of the Level 2 Physics 2024 paper for the Mechanics Standard. Make sure you've got your resource sheet open or with you. I think we need a pencil and a calculator for this exam, and a ruler, sorry. So we'll get straight into it. As ever, whenever you get to a question, I suggest you pause it, have a go first on your own, and then if you get stuck or if you're happy with what you've done, you want to just check you're working, then press play on the video. But yeah, we'll jump straight in. Question 1, momentum and circular motion. Jono and Tony are in the kitchen. Their dog is sitting on the floor next to them when the neighbour's dog comes in and playfully chases it around the table. There's obviously, I've received a picture of a dog around kitchen island there. Part A says the dog runs in a circle on the floor around the table. Add a labelled arrow to the diagram below to show the force acting on the dog as it runs in a circle at a constant speed. So despite the fact he's travelling at a constant speed, in order to travel in a circle, he must be consistently accelerating towards the centre of the circle, much in the same way the Earth is consistently pulled towards the Sun. Our centre of the circle is here. We're going to have a nice rough arrow coming in like that. And we're going to label it FC, or centripetal force, or just F. Looking at the mark scheme, they're happy basically for any force to be labelled there. Friction or FC, is what they're looking for. And that's an achieved question. Part B, we are told that the mass of the dog is 10 kilograms. The dog is moving at 0.87 meters per second, and the centripetal force is 15 newtons. So we have our M, we have a velocity V, and we have a centripetal force of 15. We're looking for an equation that involves those three quantities and the radius, which is our FC equals mv squared over our equation. We want to get the radius on its own, so we're going to multiply both sides by r, and then we'll divide both sides by FC in order to do that. Just very quickly to show all steps of our working, r is equal to mv squared over FC. Then we substitute those values in from above. 10 times 0.87 squared divided by 15. Just be careful when you're typing this into a calculator that you don't accidentally square the 10 as well. If you want, you can try and use brackets to separate it all out, but your calculator should know what you're on about if you just square the 0.87. And our calculator tells us that the answer is 0.5046 newtons. So I'm going to write the full answer and then my rounded answer. All these numbers are two significant figures, so my answer will also be two significant figures. The 6 does not round up the 4 to a 5, which then rounds it up. 46 is less than 50, so it rounds down to just 50. And that's question A and B. Oh, sorry, part I, my mistake. For part II, part 2, on the other side of the table, the dog hits a slippery patch. I'm going to just underline that on the floor, and it slides off at a tangent. Use physics principles to explain the dog's velocity immediately after it starts moving off at a tangent. So, after it's hit the slippery patch, we're told it's moving off at a tangent. I'm just going to draw a very quick tangent, a line where, in theory, it touches the circle it was already on just once. And then we have this new velocity. So, when the dog hits the slippery patch, because that's the main event that they're talking about, that's the main thing that's happened. That's what we're going to start our answer with. And the big clue here is that it's slippery. The size of the, or the amount of friction isn't specified. It's just the idea that when the dog hits the slippery patch, the size of the friction or centripetal force, decreases. Therefore, the dog's velocity will be, because we have no force pulling the dog towards the center anymore, we're assuming there's either a very small centripetal force or none at all. We are going to assume that he's traveling off in a straight line forever and a constant velocity now, because there are no more unbalanced forces on him. Therefore, the dog's velocity will be constant in the direction of the tangent as there are no unbalanced forces. And that is not meant to be a space between those two letters, my mistake. Okay, now for this question, we are just looking for the correct answer of 0.50 meters for achieved, or saying that the velocity is now constant, or in saying that the size of the centripetal or friction force has decreased. If you said both those things and got the calculation correct, this was a merit question between part 2 here and part 1 on the other side. Okay, so you had to get that answer for achieve, and you needed both the written explanation and the calculation for merit. Now for part C, what we're going to do is a bit more of a calculation. We are told that the dog slides along the floor towards Jono. Jono reaches down and cushions the dog as it slides into him by putting out his arms and then gradually bringing them in towards him. The dog takes 2 seconds to come to rest unharmed. Use physics principles to explain why Jono put his arms out to cushion the dog rather than let the dog stop quickly in 0.10 seconds. Start by calculating the force experienced by the dog in the cushioned collision. So, just got a classic question to do with this idea of collisions and therefore impulse. We're going to be using the impulse equation from your formula sheet. And I'm just going to find mine so I can put it away. There you go. Okay, so it's given us a big clue. We're starting by calculating the force experienced by the dog in the cushioned collision. We are told that the speed, I think it's on the previous page, was, I just realised I said newtons here. For part BI, it should be meters, obviously, because we're calculating the radius. My mistake. Sorry. I'm sorry. So we were told that the speed of the dog is 0.87 meters per second. That's the speed that we have to use here, because in our equation for impulse, we have that change in momentum is equal to force multiplied by the change in time. In order to get force on its own, we're going to divide both sides by delta t, and that will be equal, that will give us force equal to delta p over delta t. Our delta p is our final momentum minus our initial momentum divided by our change in time, the time elapsed, which in this case is going to be 2 seconds. For our final momentum, when the dog is at the end of the journey, speed is 0. The initial momentum is the mass of the dog multiplied by its initial velocity. And I don't remember the mass of the dog either. Sorry, it was 10 kilograms and 0.87 meters per second. And so our delta P is equal to minus 8.7 kilogram meters per second. Now, because he was initially moving, let's say, to the right, and as he slowed down, the change momentum must have been to the left. Okay, That was our change in momentum, sorry, but we still need to go back and do our change in time. Force is equal to this change in momentum minus 8.7 divided by the time that was elapsed, which equals 4.35 newtons. And again, the negative is just directional. It's just the value of the force that we're looking for. Now, what you can do is we can use a second calculation for the case where the dog stopped quickly, just as a comparison. The change in momentum will be the same, minus 8.7, but our time will now be 0.1. So f of 2 is that. F of 0.1 is equal to minus 8.7 over 0.1, which is equal to minus 87 newtons. So we can see very clearly, with the longer time it takes to stop the dog, the force is much reduced. And so in our description, we can describe that. As Jono uses his hands to slow down the dog, sorry, I apologize for that, uses his hands to slow down the dog, he increases the time taken to change momentum, reducing or lowering the force the dog experiences. Done. So there's quite a lot there. Now, these sorts of questions, you could have one where it doesn't ask or suggest that you do the calculation, and instead you just describe this last sentence with the equation F equals delta P, and you can say, if the change in momentum stays the same and the time either increases or decreases, the force will do the opposite, because the time is on the bottom of the fraction. The time gets very small, the fraction gets very big, force gets very big. But as it didn't, we don't need to worry about that. And for part C, if you calculated the momentum of 8.7 or minus 8.7 kilogram meters per second, that was achieved. Or if you stated the force would be reduced, that would be achieved as well. If you calculated the force of the 2-second collision correctly, that was merit. If you said that this is less than the quicker time elapsed situation, and if you did all of this together, this is an excellent answer. And then we're on to part D. Now, we are told that Jono releases his 10-kilogram dog and it runs directly towards the neighbour's dog at 1.1 meters per second. We've got a different velocity this time. The neighbour's dog, mass 12 kilograms, runs directly towards Jono's dog. They collide, stick together, and slide across the floor at 0.3 meters per second. They've handily given us this little diagram adapted from TikTok, where we have our unknown velocity and our masses labeled. After the impact, they've given us the combined velocity, but they haven't given us any of the masses. Now, because the dogs have stuck together in the collision, their masses simply get added together. So 12 plus 10 kilograms means that after the collision, they had a combined mass of 22 kg. Now, the question's asking us to calculate the speed the neighbour's dog was moving before the collision. So this unknown v is our target variable. Now, I like to do this as a really clear before and after. I encourage you to do the same thing. The total momentum before must be equal to the total momentum after. That's our law of conservation of momentum. That's the law that allows us to do this calculation. At some point, I am going to state it. Actually, you know what? I'm going to do it right here. total momentum, with these sorts of laws, if you're going to use a law in a question to make an answer, you should always give it as soon as you can, just because it's usually a mark in itself. Total momentum before must equal with an exclamation point just means it must be. We're setting that condition. The total momentum after. Now our total momentum is Jono's dog is this one, and the neighbour's dog is that one. So we'll have that P of N for the neighbour's dog plus P of Jono's dog must be equal to P of both. That's what our conservation of momentum equation, or law, tells us. And then we're just going to use from our formula sheet that P is equal to MB such that M of N times V of N, the neighbour's dog and the neighbour's mass, plus the same for Jono's MJ and VJ is equal to M both, V both. And then we just substitute all our values in from up top. And again, it's up to you whether you literally space it out so it matches the various sort of columns you've got underneath each object in the collision. Sometimes it's nice to do that. Sometimes with simple ones like this, it's not so important. The only thing to be aware of is that Jono's dog is running towards the other dog. So we've got one animal going to the right and the other going to the left. After the collision, they end up going to the right. Therefore, I'm going to say that my left to right is positive. Therefore, anything moving left is a negative value. So our mass of the neighbour's dog was 12. The velocity is v. We don't know what it is yet. We're trying to work that out. The mass of Jono's dog was 10. Its velocity was 1.1. But remember, it was our minus velocity. And then that must be equal to their combined mass, the mass of both dogs, multiplied by the velocity of both dogs, which was 0.3. Now it's up to you which order you do this, whether you work out or calculate these brackets individually, or you rearrange them. I'm going to rearrange them to begin with, because that's just the way I like to do it. So I want to get rid of this whole thing. Now, because there's a minus inside it, effectively this becomes a negative. Therefore, we're going to add this bracket to the other side, or add 11 if you've multiplied it out. Add 10 times 1.1 to both sides. Therefore, we get 12v is equal to 22 times 0.3. Something all muddled up here. Plus 10 times 1.1. And then we're going to divide both sides by 12. And it equals this whole thing. Which we can put into our calculator altogether. Now, the reason I've done this, I haven't done any calculation just yet, it's just because often, well, I say often, it's quite easy for people to make a little mistake when they're typing in stuff in the calculator, particularly with brackets, particularly with decimal places. Therefore, if you're doing lots of different calculations, one after the other, it just means there's a higher chance of making that mistake. If you're finding the algebra itself, the rearrangement, a bit more difficult with these bigger brackets, these bigger terms moving around, then absolutely you can calculate them and then move them around, which is my personal preference as to what to do. So we are going to times various numbers together. And we should get a velocity of 5.86 to begin with. I don't know why I wrote divide by 3. Divide by 12, obviously. Sorry. I have no idea where the 3 came from. Therefore, we get an answer of 1.46 recurring meters per second, which equals 1.5 meters per second, following the number of significant figures given to us in the question. Okay, apologise for that. That shouldn't have been a 3. I must have just read a 3 as I was writing it. We are dividing by 12 to both sides, so let's divide by 12 here, and you get 1.5. If you did all of that correctly, which I didn't, you will get excellent. If you got to if you had these momenta individually calculated, and you had stated that momentum is conserved in some way or another, that was enough for merit. And if you calculated any value of momentum, that was enough for achieve. Now, if I was marking this and I'd seen this written down, I would probably have counted it. But it's always a good idea, if you're unsure if you've done the merit excellence bits correctly, just to calculate your individual momenta. Okay, and again, this law stated is needed for merit and excellence. So same with any question where you're invoking a physics law, make sure you write it down. And then that was question 1. On to question 2. Springs and equilibrium. Tony decides to make a cake. Tony and Jono measure 0.11 kilograms of flour using a kitchen balance as shown below. There are 3 springs in the balance. Imagine there's a set of scales on there, vintage cinnamon ones. There are 3 springs in the balance. Each gets compressed 0.01 meters when the flour is added. Sorry, and there's 3 here. The simplified diagram shows the springs in the balance. Okay, and we can see that adding the flour has sunk it by 0.01 meters. We are told in part A to add labels to the diagram above right with the flour to show the 2 forces acting on the flour. Now be careful here. The flour is not in contact with the individual springs, so don't be tempted to draw 3 forces due to the springs. It's just the forces that the flour is experiencing. So I'm going to say that my flour is somewhere at the bottom of my dish. And because it's not accelerating, it's not bouncing up and down, it's not moving at all, its velocity is 0, we know the forces are balanced. Gravity is the thing holding it in the pan. Whoops. Which I've drawn through the spring not very carefully. And then the thing stopping it falling through the tray itself is the normal reaction. So make sure your lines are the same length as each other. I'm going to go over mine in pen because you can't actually see what I've drawn. But it is just the 2 lines up and down. And it's probably a good idea to make sure you do add that little node in the center just so you can see where they're starting from. And then we're going to label them Fs for support force and Fw for the weight force. You could go with Fn, Fr for normal reaction, or just write the words if you're unsure which ones to choose. Then for part B, we are told to calculate the spring constant for 1 spring. Now, when we do our calculation, because there are 3 springs here acting in parallel, we have to remember that the spring constant of them is multiplied by how many springs you have in parallel with one another. So, I'll make a big point of it as well when we get there in the calculation, but there is going to be a time when we have to divide by 3 to find the spring constant for just the 1 spring. Looking at your formula sheet, we need an equation that relates force to spring constant to the extension, which is given by Hooke's law. Now, we are not actually given the size of the force, but part A was a bit of a clue as to what to do. We know that the size of the weight force will be equal to the force pushing upwards on the flour. We know that we have 0.11 kilograms of flour, again, all the way at the start of the question. And we know what G is from our formula sheet, so we can work out the size of the weight force. So Fw equals F, so F is equal to mg which is equal to 0.1 multiplied by G, 9.8. Oops, sorry, off the page. 0.11 times 9.8 in a calculator gives us 1.078 newtons, which we can round to 1.1 newtons. Now, the reason I'm doing that rounding is because often that will be one of the first steps of an achieve mark for doing that calculation. No, I'm wrong, sorry. The mark scheme needs you to get to the spring constant, in which case, don't round. Sorry, I stand corrected. We're not going to use the rounded answer. Whenever you're using a calculated number that you yourself has calculated, you have to use the unrounded value. I've seen a few times in recent years where using rounded numbers has given you the wrong answer and people have missed out on merit and excellence for that reason. So be really careful, always use the unrounded answer in future calculations. We're trying to work out what K is from Hooke's law. So if this is Hooke's law, we're going to rearrange to get K on its own. So I'm going to divide both sides by minus X. The minus is directional. Again, it's not that significant for this question. And so we get to an equation, K is equal to F minus, divided by X, sorry. Our force is 1.078, not 1.1. And our extension is given to us earlier in the question as being 1 centimeter or 0.01 meters. Therefore, our spring constant comes out at 107.8 newtons per meter, but this is for all three springs combined. So this is the K for 3 springs. We want the K for 1 spring, which is going to equal K3 divided by 3 equals 107.8 over 3 equals, sorry, I'm calculating it, 35.93 recurring newtons per meter equals 36 newtons per meter. If we did all that together and got to this 1 spring or the single spring constant, that was merit. If you wanted to get achieve, you had to get to this point here, 107.8. So again, if you've got this sort of question where it's making use of balanced forces, often it's a bit of a clue that that's what you're going to have to use to work out the force in the subsequent calculation. And that was part B. On to part C. Oops. We're still talking about Jono. How we are. So when Jono brings the groceries to the front door, he has a choice of climbing the stairs or using the ramp. He has found that it takes less time to go up the ramp than the stairs. We've got a diagram here. We are asked to compare both routes by considering the work done, force required, and the power. Now, often with these sorts of longer written questions, you are almost required to discuss an equation, and this is looking like we have to use multiple equations in our answer. Before we start writing, therefore, I'm going to write down here what the relevant equations might be. Because we're talking about work done, force and power, those are the ones I'm going to look for. Our equation for work done is F times D. Our equation for force is, well, it's in that work done equation already. Then for our force, the equation for power, we have that power is equal to energy divided by time. On your formula sheet, I guess in this case we can have work done divided by time. Now, because our work done is calculated by doing force times distance, the size of the force to go up will be smaller for the ramp, but the distance is much greater. We can confirm this with the gain of potential energy, the gravitational potential energy equation equals mgh. Because everything about this will be the same, no matter which route they take, the energy change is the same. Therefore, the work done will remain the same. And it's because the vertical height is unchanged. Even though it's a longer distance to go, in terms of energy, ignoring other forms of energy, the height is the only thing that would affect it under mass and gravity, but the height's the same either route he goes. So, work done is the same for each route. As the vertical distance is the same. It's important to justify your answer with an actual reason why. Now, because the work done is the same, when we're thinking about the size of our force here, if we wanted to, we could rearrange this equation so it's for force instead. Force is W over D. Because the work done is the same and it's the distance that's changing, now this time we can consider the horizontal distance as well. The force will be smaller for the ramp because its distance is much larger. If the denominator gets bigger, then the size of this fraction gets smaller, therefore the force gets smaller. So the force required, nice and straightforward sentences here, force required is less for the ramp as the distance traveled is greater, but the work done is less. Is the same, which is what we just said. So the force is less as the distance goes up because work done is the same. I don't know why I wrote but either, sorry. Half asleep. So the final point we have to discuss is power. Now, power is equal to work done over time. There's no mention of time in the diagram, but at the very start of the question, we were told that he has found that it takes less time to go up the ramp than the stairs. Therefore, for the ramp, this value of t is smaller. Therefore, our value of p is bigger because the denominator gets smaller, the size of this whole fraction gets bigger, therefore p gets bigger. So, power to use the ramp is greater as the time is very similar in structure to the previous point. Power to use the ramp is greater as the time taken to ascend it has decreased. While work done stayed the same. Again, it was that first point we made. Just to be really clear, it's because the only force we're assuming he's working against is gravity, and gravity is always a vertical force. Okay. Now, if you did all three linked to a good reason, as well as the correct point made for each one, that's excellent. If you only did it for two of them, that's merit. And if you But actually, if you just had to say that either the work done stayed the same, the force goes up, or the power goes up for the ramp, sorry. If you discussed your answer in terms of the stairs instead, obviously the opposite meaning is accepted. Then we're on to part D. Now, part D now uses Tony. He's hanging up a spice rack, hanging it by wires above the workbench as shown below. We have a diagram here. The ginger spice has a mass of 0.03 kilograms, the salt 0.5 kilograms, and the uniform rack has a mass of 0.37 kilograms and is 0.4 meters long. The ginger spice is placed 0.15 meters and the salt is placed 0.05 meters from the left-hand wire, as shown below. The maximum tension force that each wire can provide is 5 newtons. Now, our diagram is sort of incomplete here. There's no question that's asking for us to add anything to the diagram, but these sorts of questions, I think, become a lot more intuitive once you can actually see what's going on everywhere. So I'm going to go through and transcribe all the information from here and add it to this diagram. There may well meant to be an actual drawing given to you in the exam, but obviously there's nothing here, it's just a blank square. So using my pencil, the ginger has a mass of 0.03 kilograms and it was placed 0.15 meters away. So our ginger is going above the 0.15 and its mass, or its weight, sorry, is 0.03 g. Just to be clear, this is not grams. We're given this number in kilograms. I'm just saying that its weight is equal to 0.03 g. The salt was half a kilogram, didn't underline it for some reason, and it was placed 0.05 meters away. It's this one here. So I'm going to add another little box, or bigger box if you want, it's a bigger mass, and it's 0.5 g this time. The uniform rack has a mass of 0.37 kilograms and is 0.4 meters long. Because it's a uniform rack, we have to assume that its center of mass is halfway along the rack. Therefore, its mass and therefore its weight acts through that center of mass, which is halfway along. So we'll have another arrow, 0.37 g, and I'm going to add my own distance arrow across, being quite messy. Because the rack is 0.4 meters long, this distance is 0.2 meters long. Now, hopefully from here, if we have our two support forces labelled, supporter A and supporter B, we can see that we've got quite a classic sort of torque question. Therefore, for part I, state the conditions required for the spice rack to be in equilibrium. We have to use our torque understanding. For the rack to be in equilibrium, the anti-clockwise torques must be equal to the clockwise torques. That is to say, or you could say differently, simply that or there is no resultant torque. Or the torques are balanced. There's a million different ways to word it, but that's the meaning you're looking for. Then for part 2, we are told that using or by performing suitable calculations, decide if the wires can hold the spice rack with the ginger and the bag of salt on. Now, we were told that the maximum tension that each one can provide is 5 newtons. That doesn't mean that the tension at each one will be 5. That's the maximum. So SA or SB, whatever one we're working out, won't necessarily be 5. We're working out those two unknowns. If they're bigger than 5, then the rack will snap, or the wires will snap, and the rack will fall. So, based on part I, our condition we've set ourselves, we have that torques clockwise must equal torques anti-clockwise. Now you can do this either left and right. I like doing it one after the other. So I'm going to do my torques clockwise, everything that's turning this system clockwise. In order to make this a lot easier and remove an algebraic term, an unknown from our equation, we should set our pivot point to either be at SA or SB. Because we're already measuring these distances from the left-hand side, it will save about 10 seconds worth of thinking. And so I'm going to say that this is my pivot point over here. Once I've set this as my pivot point, my SA is 0 meters away from it, and so its torque term vanishes, leaving us with lots of known forces and one unknown for SB. So we're going to be calculating for SB. If you're doing it the other way and you've said that this is your pivot point instead, that's absolutely fine. Just all your distances will be 0.4 minus the distances that I've written down here, because you're finding out this distance from this side to here, this side to here, this side to here. Okay, so if my pivot is at SA, then the things that are going to turn this system clockwise are, and if you find this bit conceptually hard, get your ruler or your pencil, line it up with this actual system, put your finger on it wherever the pivot point is, and then see. If these forces are pulling down on it, it's going to turn my ruler clockwise. Ergo, my SB up here is pulling it anti-clockwise. So you have this stuff with you. As I say, just line it up, press down wherever the pivot is, and then push in the direction that the force arrows are telling you. So we've got 3 forces acting clockwise, and we've got their various distances labelled on. So because our equation for torque is equal to FD, we're going to do this for each individual force and add them all together. I'm going to use lots of brackets just to be really clean with it as well. So my first force is my 0.5 G of the salt multiplied by the distance of 0.05. 0.5 G times 0.05. Close the brackets, and I'm on to my second object, my ginger? Yeah, ginger. Same idea again, 0.03 G multiplied by its distance, which was 0.15 meters. And then lastly, our center of mass was 0.2 meters away, and the weight was 0.37. Now again, I'm trying not to do any calculations until just doing it all at once. You are welcome to go by and calculate them all individually and add them together. It's just personal preference. I'm just going to make it clear that this is my tau salt, tau ginger, and tau rack. Okay, that is equal. Well, I'll type it out. Skip a few seconds if you don't want to wait. If you're not skipping ahead, just be really careful with your brackets. And remember that G is not grams, G is gravity or gravitational field strength, 9.8. And the last one, 0.37 times 9.8 times 0.2 gives me a total clockwise torque of 1.0143 Newton meters. Again, we've got force times distance, so we just combine our two units. Now, our anti-clockwise torque, it's much more straightforward. We said already that the only torque acting anti-clockwise is our SB. Therefore, it's an unknown force we're going to work out, and it's 0.4 meters away. So our anti-clockwise torque is just 0.4 SB. Now, back to our first condition, we've said that the clockwise torques must be equal to anti-clockwise, and so we can say that 1.0143, again using the unrounded number, must be equal to 0.4 SB. And if we divide both sides by 0.4, we get SB on its own. 1.143 over 0.4 is equal to 2.535 newtons, which we can round to 2.5 to checking the number of significant figures. So our size of our support force at B is 2.5 newtons. Now there's a couple of different ways you can go about working out the support force at A. Either you can do all of this again, but changing the pivot point round, or we can use a second different rule or fact about this equilibrium system, in that assuming, does it say explicitly? It's hanging there. The rack isn't accelerating upwards or downwards. Therefore, all the forces vertically must cancel out. So this time, rather than thinking about rotations with a pivot point, just thinking about these forces here, they must be providing enough of an upwards force to balance the forces downwards. So, by resolving forces vertically, we have that all the forces, the sum of forces up, must be equal to the sum of forces down. You don't need to use the sigma notation, it's just quicker than writing all of them or total. So SA plus SB must be equal to all of these weights added together. 0.5 G, I do not need to multiply by distance now. Added to 0.03 G plus 0.37 G. And because we want to work out what SA is now, we're going to subtract SB from both sides. So SA is equal to 0.53, 0.9 G minus SB. All I've done there is collected up the like terms, just like in maths. We've got lots of this time that G is our algebraic term, and so adding 0.5, 0.03, and 0.37 gives us 0.9. We've taken away SB from both sides. And we can use our unrounded SB to find that our SA is 6.284 equals 6.3 newtons. So we have our SA and our SB. If you're dead keen and you've got loads of time left from electricity as well, you can go back and check this. Doing it the torque way, that's a bit of a job. So only do that if you've got loads of time. However, this still isn't enough. We actually have to answer the question. It's not enough just to calculate it and assume the examiner will infer what you mean. We were asked to decide whether the wires can hold the spice rack or not. We're told it's hanging, but we were also told the max force was 5, we have a force of 6.3 at support A. Therefore, I've run out of space because I've wasted all this space here. 6.3 is greater than 5 newtons, obviously. So the rack will break at A. Now that last statement is really important. It is explicitly requested for excellence. So if you did all this work, all these calculations, and got 6.3 and 2.5, but didn't write that sentence, you get merit. Alternatively, if you tried to do all this and made one little mistake, or one minor error, according to the mark scheme, that's merit. Or if you stated your conditions, so the torques are balanced either here or up here, and then calculated one of the torque or one of the tensions, one of the support forces, either A and B, that was enough for a merit. For achieved, you just had to say either the conditions that they must be balanced or calculate one torque correctly. So if you wanted to if torque is your least favorite thing, just try to use one of the weights, one of the distances, and do a torque at least. Even if you're not going to try and do all of it together, try to do one because it will give you the achieve point. And that's question 2. Let's now on to question 3. Question 3 is motion. Now we are told that Tony is going to add apples to the cake. Sure. His friend Jono rolls an apple along the table. The apple leaves his hand at 0.56 meters per second and stops in front of Tony. It takes 4 seconds to roll along the table top. I'm presuming there is going to be some sort of apple in this dining table. In the photo, obviously not for us. Question A is to calculate the acceleration of the apple. Now, I forgot to underline them. This is a bit of a clue in itself, but we have a starting speed. This is the speed at which, or the velocity at which the apple left his hand, and it comes to a stop. So its final velocity is going to be 0. It takes 4 seconds to roll on the tabletop. I'm just going to add in my various algebraic symbols just to make it crystal clear to me. We're looking for acceleration. So I need one of the equations of motion that contains VI, VF, T, and A. Now, I don't know what your teachers tell you. I tell my kids to always write the 5 letters down like this, just so you can go through and fill them in crystal clear. I don't think you need to for this one necessarily, but I'm going to anyway. D is not involved. We're not given it. We don't need to find it. It's irrelevant. VI was 0.56. VF was 0. Acceleration is what we're calculating. And T is 4. This is how I got taught when I was at school. It seems like a really easy way to figure out which bits you're missing. And you can actually apply this sort of structure to any calculation question if you know the letters that the values are represented by. So looking at your formula sheet, the equation that involves those 4 is SUVAT 1, the first one. VF is equal to VI plus AT. We want the equation for A, so we're going to rearrange it. Because we've got the A as our target variable, but there's something added to it, we can't divide by T yet. We have to subtract the VI first. If you do divide by T, you just get a divided by T term here, which makes it a bit messier. It still works, but it's far more easy to do it like so. Then to get the A on its own, we divide by T. So VF becomes, or minus VI becomes VF minus VI over T, which equals 0 minus 0.56 divided by 4. which gives us minus 0.14 meters per second squared. We've got a negative answer, which is good because the apple is decelerating, it's slowing down, so we should get a negative answer, and our units are meters per second squared. Now, annoyingly, this next question has been cut across 2 pages for me. We are told, though, that Tony throws the apple to Jono. The angle of the throw is 40 degrees, the initial velocity is 5, and it's shown in the diagram below. I'm going to redraw this on the next page, just so I haven't got to flip back. And we're going from right to left this time, chaotic. That's my ground, that's my throw. And I'm going to just in pen to highlight that it's significant. This is the actual initial vector that I'm going to use. And it was 5 meters per second at an angle of 40. Calculates the vertical and horizontal components of the initial velocity. We can see here that we've got a triangle. I'm going to use a different coloured pen if I got a red one, because it's a bit brighter. The horizontal and vertical components are just the 2 sides of the triangle that the resultant vector makes. These 2. Now we can see I have a right-angled triangle. It's very small. Sorry about the drawing. I have a right-angled triangle. I have one side, the hypotenuse, and an angle, so I can work out any of the other sides. My angle is here, so this side, my horizontal velocity, is the adjacent. Therefore, my vertical velocity is the opposite side to the angle. And so I'm going to use SOHCAHTOA. If it's useful to you, you can write down SOHCAHTOA. And remember that it's opposite over hypotenuse, adjacent over hypotenuse, opposite over adjacent. So, because I want to work out both the opposite and the adjacent, I'm going to have to use both of these sine and cosine equations. So sine theta is equal to the opposite over the hypotenuse. I'm also going to be using, over on the right hand side, cosine of theta is equal to the adj over hypotenuse. And for both of them, because I want to get just the adj on its own and the op on its own, I'm going to multiply by both of them by the hypotenuse. You don't need to do it side by side like this, it's just saving me effort. And really, you shouldn't use 3 letters as algebra, but just so it's super clear that it's each side, I'm going to. Then, because we know the hypotenuse and the theta, we just have 5 sine 40 equals and 5 cosine 40 equals. Now make sure your calculator is not in radians, which mine is. If you're not sure how to do that, or you've forgotten, I've forgotten as well, press shift, set up at least these Casio ones, and then I want degrees deg. 5 sine 40 is 3.213. Oh, 9 I guess is important. Therefore, 3.2 meters per second is my vertical motion. And then my horizontal motion, VH, is equal to, again, if you get in the habit of not deleting everything on your laptop straight away, it just saves some time writing, not a lot, but yeah. 3.8302 equals 3.8 meters per second. Now you could have used Pythagoras once you had one of them to work out the missing one, but it seems far easier to do it like this. If you did both of those correctly and made it clear which one was which, that's merit. If you found either of these answers and you didn't necessarily specify whether it's horizontal or vertical, it's achieved. If you calculated both and didn't say which one was which, that was also only achieved. So just make sure you're really clear writing what your answer is actually equal to. Then part C, C part I, sorry. We have some more diagrams of the same system, but this time, bizarrely, they are going from left to right. Go figure. Start of motion here, we have the forces and the direction of velocity diagram. So at the start of the motion, because these calculations become essentially impossible for us if there is air resistance, the only force acting once the apple has started moving is gravity or weight. Now, we're assuming the apple hasn't gone high enough here, that gravity would get weaker as it got further from the Earth's surface, or center, should I say. Therefore, these arrows should be the same length. You don't have to use a ruler, just try and eyeball it and make sure they are accurate. If you label them as FG or FW, that would be fine as well. For our velocity, this is changing throughout the flight. And each time, it's going to be a tangent to the curve. So I am going to use a ruler and a pencil here just to make sure I don't make any silly mistakes. But the tangent to the curve is just where, just like with the centripetal force question, it's a straight line that continues in the direction at that instantaneous moment in the curve. The other thing to note is, at the start and at the end, the apple has both vertical and horizontal components of motion. At B, it only has horizontal motion. So at B, the arrow will be slightly shorter, but it will be essentially or roughly the horizontal length of this first arrow. I, by chance, have done it nearly to a centimetre. So I'll just draw a nice horizontal one again as a tangent. It's just sort of kissing the very top of the curve. And then by the time the apples come down here, it's very difficult to draw this because the curves are run out, but we have our tangent somewhat like so. And I've gone out of the box, but that's okay. Like that. Now, in the mark scheme, there are 3 different parts to this, and the marks are sort of given as a combination of all of them. And so I'm not going to go, I think this, if you did this correctly, that would be achieved. Yes. Oh, I've skipped part I, sorry. I'm stupid. That was part 2. Sorry, part 2. For points A, B, C on the appropriate diagram above, add labelled arrows of appropriate length to show the force, if any, acting on the apple, and the direction of the velocity of the apple. Sorry. My mistake. I didn't do part I first. That was part 2. So for part 2, if you did those arrows all correctly, either on the force or the velocity diagram, that was achieved. If you did all of these correctly, then that's a merit. Sorry, the type of motion this is, you have 2 options, either by describing the shape of the curve, which is parabolic, or what we call it in physics is it's the motion of a projectile. So projectile motion. If you said parabola, that'd be fine as well, I would presume. But yeah, so that was the achieve part. For merits, you had to do either or 2 of this, this, or this. For part 3, and this is one of those classic again sort of questions where you're describing how the vertical velocity and the horizontal velocity change throughout the flight. Now, we've sort of shown that with our diagram here, but because there's no air resistance, as we said before, the horizontal velocity remains constant. Then the vertical motion, if you imagine it, it starts off with quite a high vertical velocity. As gravity acts on the ball, it starts to lose that vertical motion until momentarily or instantaneously it has a vertical velocity of 0, which then becomes increasingly negative or decreases further from 0 to negative values. Or so down here we can say the vertical velocity decreased from, if you're really keen, you can give the starting value, which we found at the top of the page. You do not need to do this with a mark scheme, it just makes the sentence make sense. The vertical velocity decreased from 3.2 to 0, then to minus 3.2. Because it's symmetrical, geometrically symmetrical, the final velocity will be negative. But the same. Alternatively, you could have just said vertical velocity decreases or experiences constant acceleration downwards. Now this question is a bit weird because usually I've seen them where like this sort of question would be excellence on its own. Because of all this other stuff it's been combined with, the diagrams and naming it, you only need to give these 2 points. There's not a lot of spaces, which is a bit of a clue that you don't need to do that. But if you, I would understand if you had written loads for this. You just didn't need to. If you did the explanation correctly, your diagrams correctly, and named the type of motion, that was an achieved. As I said, if you just did any 2 of these, that was merit. Merit doesn't actually... Oh no, sorry, I'm misreading it. You have to get both of these right and the name, or the correct descriptions down here, and the 2 diagrams, or the definition as well for merit. For achieved, there's a long list of stuff. Either you gave the right name here, you gave the right force diagram, the right velocity diagrams, or said horizontal velocity remains constant in part 3, or said that the vertical velocity is consistently decreasing due to gravity. And then that was 3C. Last part, it's a bit of a long video, sorry about that. We are told that the ceiling, I don't know why it's not focusing, oh, there you go. The ceiling is 1.5 meters above the table surface. By calculating the maximum height reached by the apple as well as the horizontal distance covered, determine whether the apple will reach only 2 meters away. And again, this is a really classic sort of question. I'm gonna just draw very quickly the system. Starting at starting at 5 meters per second. We do not need to calculate the components because we've already worked them out like that. So I have to flick back to our previous page in a sec. Now with these sorts of questions, because the only force acting on the apple is gravity, we're assuming there's no air resistance, we cannot calculate this if there is. The thing that dictates how long the apple is in the air for is the vertical motion. The horizontal motion remains constant. So in order to work out how long the apple is in the air for, therefore how far can it fly, we have to work out the time. We can only do that vertically. So there's going to be a fair bit to do. I'm going to do side-by-side stuff, vertical motion and horizontal, just to keep it nice and clean and clear as to what I'm doing. You can set it out with like paragraphs. You could use the whole back page, up to you. I'm going to do it this way. So my vertical motion just like before, D, VI, VF, A, and T are all written down. The first thing it wants me to do, I know I started talking about time, it wants us to calculate the maximum height reached by the apple. Therefore, I want to work out the vertical distance travelled. My initial velocity vertically was 3.2 from question B, and it's positive because it's moving upwards. When the apple's reached its maximum height, it will have a velocity of 0 vertically, so our VF is going to be 0, and our acceleration due to gravity is 9.8. I always do left to right as positive and upwards as positive for these values. Some people I know prefer to have acceleration as positive. To me, it's just like the opposite to a graph, so it doesn't make any sense to do that. But same idea, you get the same answer. We don't need t yet, so I'm going to cross it out. Then I need an equation that links together d via I, vf, and a. That equation is vf squared equals vi squared plus 2ad. I want to get d on its own, so I'm going to try and speed up. So we're going to divide both, I'm going to subtract from both sides vi squared, because again, we have to get rid of the stuff that's added to the desired term or the desired variable before we can do anything else. So some intense police chase going on outside. 2at, then I'm going to divide both sides by 2a, giving me an equation for d, which reads vf squared minus vi squared over 2a. Then I can put all my values in, which is 0 squared minus 3.2 squared. We should really be using the unrounded number. What was that? 32139. I have to recalculate that down. Divided by 2a, which is minus 9.8 times 2. Then I'm going to pump that all into a calculator. I am going to actually recalculate 5 sine 40 to get my accurate VI. And I suggest you do the same as well. 5 sine 40 all squared divided by minus 19.6 gives me 0.53. I was checking that's right before I go any further. Yes, it is. Nice. Equals 0.527 equals 0.53 meters. Now, annoyingly, the mark scheme has used the unrounded number here. They often try and trip people up with that. That's annoying. I would always use the unrounded answer. That should always be awarded. You should get credit for that. Anyway, sorry. That is our maximum height reached. So, it's not going to hit the ceiling, I think. So, Apple will not hit ceiling, just in case that is a desired sentence. Now, in order to work out the horizontal distance travelled, which is the other part we're asked for, we still need to use vertical motion to get time. So, I'm going to rewrite my d, vi, vf, a, and t. This time, I would like to find out time. It's always good practice to never reuse an answer that you've calculated, just in case you've made a mistake or a typo, you fat-fingered a calculator, whatever it is. Always use values you've been given if you have a choice. So I'm not going to use D, I'm going to use this. Now the only stipulation, I'll show you what I mean by that, show you what I mean in a sec, with that is if you have a VF that is non-zero and you're trying to find T, you're going to get into a situation with a quadratic. If you're not confident solving quadratics, maybe you should then try to use D. But yeah, in theory, they'll never make you do that. So I need an equation for T linking together these values, which is going to be, We don't need to. Don't use D. That's why, sorry. If you use D, you'd get a quadratic. As it stands, you won't. Vf is equal to Vi plus At. Therefore, T is equal to Vf minus Vi over A. The two steps there are subtracting Vi and then dividing by A. I'm going to be quick because I am talking a lot. Let me put the numbers in. 0 minus 3.2 over minus 9.8 equals minus 3.2 over minus 9.8. And that gives us a time of 0.3653 seconds equals 0.33 seconds. Now I can go up to my horizontal motion and I'm going to use that, and speed is distance over time. Because I've got a constant velocity, I can use the simplified form. If I was being really thorough, I would again write out this and do it for horizontal motion, where I would find that distance is what I'm looking for. My VI as my horizontal motion from the previous part, 3.8. And again, you should use the unrounded answer. I know that the mark scheme's leading us astray, but I'm going to do it anyway. 3, oh my God, 0, 2, VF is exactly the same because there is no horizontal acceleration. And we've just worked out the time to be 0.32653. If you do it this way, you still get the same equation, the way that the Subat equations work, the equations of motion. You always can arrive back at these nice simple ones. Long way short, D is this distance is velocity times time. Therefore, is 0.326 times by our velocity of 3.8302 equals 1.2506 equals 1.25 meters. Oh, I've been this is a really instructive point for you guys. My mistake, sorry. We've worked out the time for it to get to the top of its journey. Sorry, I've completely skipped ahead. I'm going to cut this back. Sorry, ignore this. If you're seeing this now, this time that we've calculated here is for it to get to a final vertical velocity of 0, which occurs here at halfway. Therefore, if the time to get here, from here to here, is 0.33, the time to get all the way to the other side is 0.66. Or if you use the unrounded number, 65, which is why you should always use the unrounded number. So, in this working that I did by mistake, just ignore that, we have time is 0.6530. Then my answer here is going to be doubled because I was silly and forgot my own little secret. Equals 2.5 meters. Tony was 2 meters away. In theory, he is thrown at 2.5 meters. So the apple will reach Tony. And it will not hit the ceiling. Sorry, I don't know how I'm going to edit this all together, but yeah. For that last question, excellence was that you gave the correct answer, it will get to him, and you showed that it won't hit the ceiling and it will go far enough. If you calculated the range, so this horizontal distance, not 1.25, it was 2.5, that is merit. And if you found either the time of 0.3, this bit down here, or the vertical motion here, that's achieved. And then that is the 2024 paper.